Today we will discuss the Terrain Relative Navigation System, or TRN system, that is going to be used on NASA's Mars 2020 rover. So what is TRN? TRN is a closed-loop control system that uses terrain measurements to estimate position. It basically decides where the rover will land without putting it in a rocky or dangerous place on Mars. So how does it work? It works by using maps created by existing satellites that are already orbiting Mars, and then stores those maps on the computer. When it's coming in for a landing, it takes pictures and compares those pictures to the maps and finds out its position from there. And from there, it decides where it wants to go. So this wasn't used on the Mars Science Laboratory, or Curiosity as it's commonly known by. MSL just used terrain measurements after it's separated from the parachute to avoid dangerous areas. And this meant that it had to be released at a lower altitude, which is riskier because the rover is closer to the ground and has a smaller margin of error. With TRN, the rover can be released from a higher altitude and have more time to land and find a safe location. To use TRN, all that needs to be known are the mass, acceleration, and time of the craft, and also the gravity on Mars, and then that can be plugged into these equations. So TRN is a discrete system because of the countable number of states. So either it's going to land or it's going to find somewhere else to go. And to find out if how it's going to do that is it uses the built-in terrain map, and from that its output is going to be a direction change to divert it to somewhere else. So in order to use this terrain data, the rover needs to filter out the noise. And to filter it out, it uses a Kalman filter, which is pretty common on guidance, navigation, and control systems. But what's special about this case is that this filter uses propagation and update functions due to the constant stream of data that the rover is measuring as it descends. This makes it an extended Kalman filter. After the data is filtered, it can then be fed into the rover's PID control system to decide how much thrust is necessary to move. And the controllers measure the error between where the rover wants to go and where the rover is at that moment, and then uses the thrusters to move closer to where it wants to go. Here's a schematic of how the system works. So the input is the terrain data and the maps, and then that is fed into the PID controller after it's being filtered. And the PID decides how far it is from the location that it wants to go and feeds that into the dynamic system. And the dynamics figure out the amount of thrust and how far the thrusters need to actuate. So then that's put into the output, and then images are taken, which is then fed back into the loop. And that system is done consistently until the rover reaches the ground. There are some errors with the system, and navigation error can be found using this formula, the PNAV formula. However, the most important performance metric is relative navigation because it shows how well the rover can navigate to the landing site. Here are the coordinate frames used on the Mars 2020 mission. A Mars-centered reference frame would be used because the planet is spinning and the landing site is essentially spinning with it. That's from the perspective of the rover as it's coming in for a landing. And here are the references that we used for all this information, and we hope that you enjoyed the video and that you learned something about the terrain relative navigation system used on the Mars 2020 mission.